Well, we continue with the talk entitled Richest Optimization with Noisy Zeroth Order Information by Sebastien Bubeck.
Thank you very much for the invitation. I'm really happy to talk here. So I'm going to tell you about mostly about a paper which is quite old now, almost 5 years old, but I think many of you don't know about it, and it could maybe be of interest to some of you. And towards the end, I'm going to state a new result. Okay, so what do I want to do? So my story begins with a metric space. So I have a metric space xd. So d is a metric and x is a space, and I have a function f, a real values function defined on this metric space. And my goal is to maximize this function. So my goal is simply to maximize f. And I'm going to assume that I'm in a black box model, so I don't know, the function f is unknown to me. But I have access to function values. Okay, so I'm going to assume that I'm in a zeroth order oracle model, so I want to maximize f using n function values queries. All right. Now, in this model, so many people have been looking at this model. So I'm going to assume that these function values queries are noisy. Okay, so n noisy function values queries. So what does it mean? It means that I can input a point x in my metric space. I put it in my black box. Okay, and what it outputs is a function value f of x plus some noise psi. Okay, and I'm going to assume that the noise psi is 0 mean, so the expectation of psi is 0, and that the tails are sub-Gaussian. Okay, so psi is sub-Gaussian. Now, of course, right now, I said nothing about the function f, so there is no way that I'm going to solve this problem in complete generality. I need to assume something about the smoothness of f. So some people actually in this room have been looking at this problem, and they make the assumption that the function f is convex, just like in the first order oracle model. But I would argue that in this model, it doesn't really make sense to assume that f is convex. Why? Because in this type of application, you should really think that here what you are doing is that you are doing an experiment. In real life, you are really trying a value x, you are making the experiment, and then you observe something at the end. So this function f, in the application that I have in mind for this problem, they are not human engineered. Okay, so assuming convexity would be that we assume that the nature is nice with us and nature is providing us with convex function, which I think is not the case. So just to give you some example of applications, one simple example would be that I'm doing some chemical reaction and I can tune different parameters. For instance, I don't know, the temperature or the concentration of some chemical components. Okay, so I have a few parameters that I can tune. I can actually do the experiment in the real life, and I observe the output, and what I want is to maximize this output. So I can try different set of values for the parameters, and that will give me different outputs. And making a convexity assumption in this case usually is just not reasonable. Another type of application for this problem would be I'm trying to tune some algorithm. So I have an algorithm that depends on a few parameters, okay, that I can tune as I want. And I don't know what are the best values for these parameters. I can try different parameters, run the algorithm on a certain data set, I get some answer at the end, a percentage of accuracy or something, and what I want is to find the best parameters for my algorithm. Again, making a convexity assumption in this setting is not very reasonable. So what I'm going to assume instead is just that the function is Lipschitz. Okay, I started with a metric space. Right now the metric didn't appear. The metric is going to appear because I'm going to assume that f is 1 Lipschitz. F is 1 Lipschitz. Of course, what does it mean? It just means that if I take two values, x and y, then this difference is bounded by the distance between x and y. All right, and I think this is a more reasonable assumption in many of the problems that this setting can tackle.
Okay. So the Lipschitz constant is known and equal to 1.
Exactly. But it's, of course, if the Lipschitz is not 1, if the Lipschitz is L, you just replace d by d times L. So This is with full generality. Alright, so now I'm going to tell you an algorithm for this problem.
An algorithm finds a local maximum.
No, a global maximum. That's the point. You don't want to do local optimization, you want to actually find the global maximum. Alright, so this algorithm is called HOO, or hierarchical optimistic optimization, and it's a joint work with Rémi Munoz, Gilles Stolz, and Csaba Szepesvári, which goes back to 08. Alright, so I'm going to make first an assumption on my metric space that I'm going to call this the assumption star. And the assumption is going to be that I can cover my metric space with a tree. Okay, so I'm going to assume that there exists a sequence of subset PHI, where H is going to be a scaling parameter, H is positive, it's an integer, and I runs from 1 to 2 to the H. So it's a sequence of subsets of X with the following property, such that. So the first property is going to be that the first element in this sequence is the entire set. So P01 is X. Okay, so at scale 0, I just see the entire space. Now I'm going to make a refinement assumption, which is that at scale H plus 1, I'm refining what I was seeing at scale H. Okay, so PHI. It can be decomposed at scale H plus 1 as PH plus 1. Let's say 2i minus 1, and disjoint union with PH plus 1, 2i. Okay? So what this means is that, so at scale 0, I see the entire space, that's P01, and now at a certain scale H, this could be PHI, and at scale H plus 1, this guy is going to be divided into two parts. Okay? This is going to be PH plus 1, 2i minus 1, and this is PH plus 1, 2i. Okay? So the way to see this is really as a tree. You see, here you start at scale 0, you have P01, and then you divide it into two parts. P11 and P12. Okay, and so on. You divide it like that. Alright, so far this is not really an assumption. And now I'm going to make an assumption on how the size of this set is shrinking. So I'm going to assume that the sets are shrinking in the sense that the diameter of PHI shrinks at a rate which is exponential. So the diameter of this guy is going to be smaller than some rho to the h, okay, where rho is a fixed parameter. Okay, so this is star with two parameters, rho which is going to be a constant, rho and nu which are two constants in 0, 1. Okay, so rho, I don't know, it could be 1/2 or something. So the size of the set are shrinking at an exponential rate. Right? And the fourth assumption is that these sets are not too small. Okay, so they contain a small ball of approximately this size. So there exists a point, there also exists a point x in PHI, such that a ball of center x and radius nu times rho to the h is contained in PHI. Alright, so that's going to be my assumption about the metric space. Is that okay with everybody? So at the end I'm going to come back to this assumption, and the new result will be that I can restate this assumption in terms of something which is much more familiar to many people. Alright, but now I'm going to work with this assumption.
So I summarize. So
Yes.
you are interested to estimate, in fact, the supremum norm of the regression function.
Yes.
Design is random or not?
No, I'm going to choose the design. So that's the point. Design is going to be adaptive, and I'm going to be able to choose sequentially my n queries.
Okay,
That's
so
going
you
to be
have a compact metric space.
It doesn't have to be compact. It has to be bounded because of this assumption, but I didn't say anything about closedness. So it is bounded, that's for sure.
Okay.
Do you have an intuitive example of
set like this satisfies your tree-like assumption?
Yeah, any bounded set in RD. Any bounded set in finite dimension.
Why do you need the Lipschitz property?
This one? On the
Lipschitz
function?
property of the function.
Right. So if the function is not Lipschitz, there is really nothing that I can say. Like there could be a spike, like in dimension 1, okay? I'm optimizing over 0, 1.
If the continuity will be enough?
No, continuity would not be enough to get a rate. Of course not, because I can always
Okay,
put
to
a
get
spike.
rate, no, but okay, to get any kind of further assumptions will be enough to get rate.
Of course, yeah. Yes, that's true. That's true. So I can generalize to Hölder, but for the sake of simplicity, I'm focusing right now on Lipschitz with respect to this metric. But continuity is definitely not enough.
Are you gonna make, is your bound gonna be explicitly new or is it constant?
Of course, it's going to be explicitly new. Because new could depend on the dimension. If you are in RD, rho and nu will depend on the dimension. There won't be numerical constant. They will depend on the shape of the set, etc. Anything else before I move on to the algorithm?
Can you check for your property computational efficient?
Yes. So the new result, the 2013 result, will be about what this exactly means. And I don't want to spoil you right now, but I will tell you. Okay. So I have this assumption. I have this assumption on my sets, and I'm going to use this tree. I'm going to use it in the following way. So what I'm going to do is that I'm going to give you an estimate of the maximum within one of these subsets. Okay, so the question is, what is a good estimate for the max of the function f of x when x is restricted to the set phi? Okay, I want, as part of my algorithm, I need estimate for this. Okay, so I have this set, right, and I made already some queries. Okay, so I'm going to assume that x1 up to xt are the queries that I made in this set x, and I observed y1 up to yt. Okay, so these guys yt is f of xt plus some noise xt. Okay, so I want to estimate the max of the function in that subset. The first thing that I could look at is the average of the function values that I obtain in this set. Okay, so let me define thi of t. That's a counter which counts how many points I have in the set phi. So it's a sum for s equals 1 to t of the indicators that xs was in the set phi. And now I'm going to define my let's say, f bar hat. It's not very nice, but so the bar means averaged, and hi means averaged over this set. So let's just call it f hat. So f hat of hit, this is the average of the values that I observe in the set phi. So it's 1 over t hi of t, sum for s equals 1 t of ys indicators that xs was in phi. So what can I say about this function value? Well, maybe it's going to be an estimate for the mean of f of x in phi, or at least it's going to be an upper bound on the minimal value of f of x up to some random fluctuations. And I know exactly what are going to be the random fluctuations because I made an assumption that the noise is sub-Gaussian. So I can say that with high probability, f hat hi of t plus a confidence bound given by Hövding, which is the square root of, let's say, 2 log t over t hit. This is going to be with high probability an upper bound on the minimal value of f of x when x is in phi. Right? You all agree with me on that? Here I just put for the confidence something like 1 over t to the 4. Okay. Alright, so this is an upper bound on the minimal value. But now I want to estimate the max. So what I need to add, because the function is Lipschitz, I need to add the diameter of the set. Okay, the diameter of phi. Now if I add plus the diameter of phi, then it's not an upper bound on the minimal value that I have, but it's an upper bound on the maximal value. Okay, so for any set in my decomposition, I can define an upper confidence bound on the true maximum within that region. Okay, and I'm going to define this, I'm going to give it a name, I'm going to call it UHI of T. Okay.
Why not to use the usual kernel smoothing?
Right.
With indicator if you want. So locally. And after that takes the maximum over the point.
So this is basically what I'm doing, right?
No, so it's not good if you use where you consider the first part, because it's your space X. It's too large to add the geometry.
So
it's constant.
What I'm doing is I'm doing this at every scale.
Yeah, I understand, but the initial step seems not to be good.
Absolutely. So now the key trick, you already see it, but so the key trick is going to combine all the scales. Okay, so now I have something at every scale, and I'm going to combine everything to get one good estimator of the max within each region. So let me write it, and then we will see if you agree with that. So now, this is not going to be my estimator for the max. Okay, this is the first rough estimate, and now I'm going to refine it as follows. So you see, let's say I have my function, right, like this. And I'm trying to estimate the maximum over this set, phi. And I came up with an upper bound, which is something which is above the function on this interval. But what I could do is that I could divide this guy, look at the next scale, at scale h plus 1, and at scale h plus 1 I can repeat this argument. And I will get other upper bounds. Maybe they will be smaller. Maybe I will get something like this at scale h plus 1. And now I can refine, because I know that an upper bound on the maximum within that subset is the maximum between these two upper bounds. So now I can refine and take the minimal value between the upper bound that I can get at scale h and the maximum of the upper bounds that I can get at scale h plus 1. So now I could look at the minimum between this upper bound, UHI of T, and the maximum between U h plus 1 to I minus 1 of T, and U h plus 1 to I of T. Okay, that would be better, right? Now I'm using information at scale h and information at scale h plus 1. But now what about scale h plus 2, h plus 3, etc.? So now the trick is to define recursively bounds that we call b values, bhi of t. It's going to be defined by this equation, except that here I put a b. Okay, and of course at the leaves, the b are the same as the u. So now I come back, I backtrack my b values, and I get an estimate at every scale which is using all the scales at once. So now I have a b value for every set. Is it clear? Maybe I went a little bit fast in this one. So again, the only thing that I'm doing here is that I'm writing in a nice way the fact that here I can take the minimum value between the scale h and the max between the scale h plus 1. And at scale h plus 1, I can take the minimal value between the scale h plus 1 and the max of the scale h plus 2, etc. So I can backtrack everything like this.
Sorry, why is the max? T belongs to only one of the two, right?
So t is the time. I'm looking for the max over this set, right? Over this set phi. Now I divide the set into two parts. Now the max is in one of the two, but I have no idea in which one. So the best I can say is that it's going to be below the max within the two subsets. Okay, so now I have b values everywhere in my tree. Now what I want to tell you is how do you choose the next query point? How do you choose xt plus 1? And the way you are going to choose it is going to be very simple. You start at the root of the tree. Okay, so you have this infinite tree, but this infinite tree, it's actually finite. Okay, it's of size t right now, because if you go below, you have no observation. So you have this infinite tree, and what you are going to do is that now you are going to follow a path where at every node you select the children which have the largest b value. So you select the part of the space which looks the most promising. Okay, the one where you believe that the max could be higher than in the other one. Okay, so if the b value in that part of the space is larger than this one, then I go here. Now I cut into two parts, and I look, is this B value larger than this one? If this is this one, then I go here, I cut, etc. And I stop. At some point I will encounter a node which corresponds to some subset of the space, where I have no point. I made no queries. And now I make my query xt plus 1 in that part of the space. Okay, so I repeat. So xt plus 1. Okay, so xt plus 1 is chosen by following a path of largest B values and stopping at an empty node and stopping at an empty node. And that defines entirely the algorithm. Okay, now I make a query, and now I'm going to update all of the B values. Okay, so the complexity in the end for n function evaluation could be quadratic in n. Okay, it could be n squared, and I will discuss it. All right, is the algorithm clear?
So
yes.
But we run like into kind of a multiple hypothesis testing. All of your bounds are probabilistic.
Yes.
So if you made a big mistake at the very first step, you got an extremely low value.
Absolutely. So yeah, but this is not an issue because everything is going to be like all of these upper bounds are going to be correct with overwhelming probabilities. Like there will be a probability of 1 over n squared that you fail.
Your bounds depend on how many points you sample.
Yes.
Okay.
Yeah,
So you up.
Exactly, and I update everything. I'm doing a union now. Okay. So now what can I prove about this? Because right now I tell you an algorithm, but maybe it's doing nothing. Maybe it's ending up in a local minimum. So it's not. And the theorem is as follows. So the theorem is that if I take T to be uniform over 1 to n, okay, so I take a time uniformly at random, I look at the best point, so f of x star, and I compare to the expectation of f at xt, x capital T. Then this is going to be bounded by some numerical constant times k log n over n to the 1 over d plus 2, where I assume that if I try to cover the set of epsilon optimal points, so not epsilon optimal point, but this is where nu is going to appear, the set of epsilon over nu optimal points. If I try to cover this set with balls of size epsilon in the metric d, I want this to be of order k over epsilon to the d. So if I have this bound on the size of the optimal guy, then I can say that I find the global optimum up to this accuracy. Okay, and then what we could do now is we could discuss this bound in details and see what exactly it means. So in the worst case, if you're in dimension d, this d could be the true dimension. And then you suffer the curse of dimensionality, right? You need n to be exponential in the true dimension for this to be small. But of course, I mean, there is no, I'm not claiming that there is any magic, right? I'm trying to optimize the Lipschitz function. This is just a difficult problem. Okay, you will not solve this in dimension 10. That's not possible. You will solve it maybe in dimension 3, maybe in dimension 4, and then I don't know. But all the interesting problems are in this, I mean, many interesting problems for this setting, for zeroth order optimization, are inherently in the small dimension. Okay, so that's a theorem from 2008. And now I just want to tell you about a new result, which is what does it mean to have this tree of partitions?
Why is it not true for all t's?
What is not true for all t?
I don't know, you took t at random.
Oh, right. Because you know it's always the same thing. You show it for the cumulative regret. So you show this bound, it's the same for gradient descent, for anything. You show that actually the sum of the f of xt minus f of x star, I mean the average of this is smaller than something. So this is exactly, you take it at random. we cannot say anything about one particular point. Okay. Alright, so now, what does it mean to have this tree of partitions? So the new theorem is as follows. So it says that star, so the assumption star is exactly equivalent to saying that my metric space XD can be embedded with distortion 1 over nu times rho into a Hilbert space. So, okay, so what does this notation mean? So that's coming back to Alex's talk this morning with the Banach-Mazur distance. So notation, we say that if we have a metric space X with a metric dx, that guy embeds in Y with a metric dy with distortion capital D if there exists a scaling parameter lambda and a mapping function psi, which goes from X to Y, such that, so if I look at the distance in X between 2 points, X and Y, okay, and I rescale it by lambda, so I rescale everything by lambda, then this is well approximated by the distance in Y once I have mapped points with psi. Okay, so this is in between dy of psi of X and psi of Y. And capital D times dy psi of X and psi of Y. So coming back to Alex's talk this morning, Alex was talking about norms here, and he was talking about the Banach-Mazur distance, and that's just the generalization to arbitrary metric space. Now if you have a norm, you're in a vector space, and actually you don't need this lambda, because you can just put the lambda in the psi, but that's not very important. Okay, so is the definition clear? What it means is that here usually what you do is that you start with an arbitrary metric space, and on the right hand side you have something that you know. Okay, for instance, a Hilbert space where you have angles and scalar product and everything. And when you say that you can embed it with distortion D, it means that even though this guy is more or less arbitrary, you can look at it up to this error as if it was in Y with dy. Okay, so here what I'm saying is that my assumption essentially means that I'm in a Hilbert space. Okay, so I'm not going beyond Euclidean optimization. Okay, everything what I'm doing might look more general, but it's not. Okay, it's exactly this. And I have maybe 5 minutes for the proof because it's a nice proof. I think it's really easy, completely elementary.
So it's the proof of what? Sorry.
The proof of this.
Okay.
Just one direction. So this one is easy. You just, well, we did it basically in the 2008 paper. If you are in the Euclidean space, you can find this type of trees. Now let's see the other direction. So the proof of this direction. So I start with this tree, and I want to show that I can embed in a Hilbert space. So what I'm going to show actually is that XD embeds in a neutral metric space with distortion 1 over nu rho. So what is a neutral metric space? It's just a metric space where instead of the triangle inequality, I have something stronger. Okay, so I'm saying that the distance between X and Y has to be bounded by the maximum between the distance of X to Z and the distance of Y to Z. Okay, so it's more restrictive than a metric space, and it has many nice properties. Basically, the important property is that if you look at balls of a fixed radius, then all the balls are disjoint. Okay, so how to see that? So you have a point X with the ball of radius, let's say R. And let's say you have a ball, so of course this picture is completely wrong. Okay, I'm going to show that this cannot happen. You have a ball, another ball of radius R. Okay, and let's assume that they overlap at some point. I'm going to show that if they overlap like this, then they must collapse. So how do you do that? Well, since they overlap, there is a point here in between. Okay. Now let's take another point here. So I know that the distance the distance from this point to this one is smaller than R because I'm in this ball. And I want to show that the distance from this one to this one is also smaller than R. So that this one is actually in this ball. So let's do it. So I can go from this one to this one, it takes me R. Then I can go from here to here, it takes me R. So by the ultrametric property, I can go from here to here, and it takes me R. Now to go from here to here, it takes me R. And I just proved that to go from here to here, it takes me R. So by the ultrametric property, to go from here to here, it takes me R. Okay, so this guy must be actually here. So if there is a point that overlaps, I can use it as a gate, basically, and the two balls are the same. Okay, so now balls are disjoint of a fixed radius, and using that you can show that the ultrametric actually embeds with distortion 1 in a Hilbert space. How do you do it? You just build a Hilbert space where the balls form an orthonormal basis. Okay, so every ball is going to be an element of the orthonormal basis. So this is well known. And I basically proved it. And now I need to show this one. And this one is going to be also easy because the intuition is that an ultrametric is a tree. Why? Well, basically a ball in an ultrametric is a subtree. A ball of a fixed radius is a subtree at a fixed depth. Okay, so I have a fixed depth like this. And you see, now if I'm taking a fixed radius, that means that I'm taking a fixed depth. And of course the subtree at a fixed depth, they are disjoint. But now here I just put on X a tree like this, and I'm going to use it to define an ultrametric. So the way I do it is that I define the distance delta between X and Y as rho to the H between X and Y, where H of XY is the max, it's the maximum depth such that the subset that contains X at depth H is the same as the subset that contains Y at depth H. So it's a max over H positive such that PHX, which is the element PHI that contains X, is equal to PHY. Okay? So this defines an ultrametric. It's easy to see, yeah, one more minute. It's easy to see that this defines an ultrametric because the balls are exactly going to be subtrees. Okay? And it's easy also to see that it's equivalent up to nu rho to the original distance by definition of the tree. Right? Why? Because the distance between X and Y, since they are equal up to this depth, that means that they are both fall in PHI, which is of diameter smaller than rho to the H. So the distance between X and Y must be smaller than rho to the H XY. And since at depth H plus 1 they are not in the same, and there is a ball of size nu times rho to the H, it means that this distance must be larger than nu times rho to the H XY plus 1, which exactly means that the two metric are the same up to this distortion. Alright, so that ends the proof, and now let me just say that now what this shows is that we didn't go beyond the Euclidean structure. So now the open question is to do Lipschitz optimization, but beyond Hilbert spaces, when you don't have an embedding like that. And I'm going to stop here. Thank you.
Okay, thank you very much. It's time for one and very short question. Please.
So if I understood correctly,
Yes.
in fact the planning of experiments doesn't bring any improvement in the rate, because it's exactly the supremum norm rate which can be obtained by...
No, it does, because you see, it doesn't in the worst case, but here I'm not in the worst case. You see, what I was doing is that I was covering the set of epsilon optimal points, not the entire set. I was not saying, I mean that's the key point, but I didn't want to spend too much time on it. What I said is that the condition is that this guy, x epsilon, so the set of points in X which are epsilon optimal, they can be covered by something of size 1 over epsilon to the d. Okay? So it could be sometimes that you are in dimension d, but this d that comes up in the proof could be 0. For instance, if you have a function that looks like this, and then it's doing something really complicated here, but around the maximum it's a peak, then d is 0 and the rate is 1 over square root n. But in terms of regression and in terms of estimation in subnorm, this is going to be a very difficult function. But in terms of maximization, it's not going to be difficult because I only care about what happens near the maximum.
But you suppose that your function is Lipschitz. This function is not Lipschitz continuous.
No,
No,
It depends on.
No, I just compare your theory. You have a ring.
Yes.
If we consider, for example, d-dimensional Euclidean space for simplicity, to keep the same letter d, then it's exactly the rate which then you can estimate the maximum of the function.
No.
If you observe, no, it's
So no, because
right.
you see, when you are trying to estimate in subnorm, you want to estimate the function everywhere, okay? And it could have variations which are bad here, right? Even still Lipschitz, but it could be difficult variation. Okay, it could be variation like this. You see, you have a big peak, and then here you have small peaks.
So the maximum of the function can be estimated with the same rate as the supremum. This is a
Yes.
this is a known thing.
And I can do better.
But the formula you write is exactly the same.
No. But I think we are.
If the t equal to 1, for simplicity, you have a 1/3.
Yes.
The rate. Log n over n as the power 1/3. It's exactly the rate.
Yes, but no, because because even in dimension 1, my d could be 0, whereas your d is always going to be 1. And my d could be 0 because I can avoid the situation. Basically,
So if you have a maximum which is
Exactly,
very, a maximum which is very, very like a boundary with a plateau, and as well it's like a sinusoid, you
yes,
better.
exactly. That's exactly.
Well, let us thank the speaker again.